In section 3.3, we're going to look at using standard algebraic techniques to solve trigonometric equations. We're going to solve trigonometric equations that are in a quadratic form. We're going to solve trigonometric equations that involve multiple angles. And we're going to use inverse trig functions to solve trigonometric equations. So when we talk about solving trigonometric equations, we're going to work with some of our standard algebraic methods when we can, like finding like terms, factoring, things like that. Our primary goal in solving a trigonometric equation is to isolate the trigonometric function, right? Isolate the trigonometric function on one side of the equation. And the example they're giving here is that to solve the equation 2 times the sine of x is equal to 1, divide each side by 2, which isolates our trigonometric equation on one side of the equation. But then when we solve it, it's important to know that there often isn't just one solution. So we know where are the angles where sine is equal to 1/2. Sine again is related to the y. Is related to the y coordinate from the unit circle. So where the y coordinate was 1/2 would be over here, and also over here on the other side. So this one would be 30 degrees, and this one over here would be 150 degrees. Or if we were working in radians, it would be pi over 6 or 5 pi over 6. And then every time we went around the circle, right, would be 2 pi. Actually, I would normally write it as 2 pi n. They wrote it as 2n pi. But remember, 2 pi is another time around the circle. Then we'll be coterminal, and we will have that again. So you could do this in radians. You could have done it in degrees. Typically, you're going to find the book's going to work in radians. All right, so what we have is to some extent an infinite number of angles because of the nature of coterminal angles. But by adding 2 pi n to the end to my solution, each of my solutions, I account for all the different solutions. And this is what it looks like if you think about it graphically, right? If we graphed it and we were looking where the sine curve hit 1/2, this line would, in each period, hit the graph twice in each period. Okay, and equally, like I described in the unit circle, this is what it looks like as well. But each time I go around the unit circle one more time, bad pen. Each time I go around the unit circle one more time, I'm going to have a coterminal angle with the exact same value as that, and the same on this one when I go around again. That's why we have to account for it with 2 pi n. Okay, so let's go ahead and do a problem. Remember, the first thing I want to do is I want to isolate my trig function on one side of the equation. So I'm going to add sine of x. So sine of x plus sine of x is 2 sine of x. I'm going to add root 2 to either side. So I get root 2 on the other side. And I'm going to divide by 2. Sine of x is equal to root 2 over 2. Okay, so again, when we think about the unit circle, root 2 where the y coordinate is root 2 over 2, and that's here at 45 degrees, which is also pi over 4. And over here at 135 degrees, which is, 1 pi, 2 pi, 3 pi over 4. And if I want to then account for all the coterminal angles, I'll have 3 pi over 4 plus or minus 2 pi n. And I'll also have the original solution, pi over 4 plus or minus 2 pi n. And that would be my solution. Okay, moving on, same idea here. I'm going to add 3 to either side, so I'll have 4 sine squared x is equal to 3. To continue to isolate sine, I'm going to divide by 4. And then I'm going to take the square root of either side. square root of 3/4 would be root 3 over the square root of 4, which is 2. So root 3 over 2. Going back to our unit circle, so you must be getting a trend here. Up here is where the y-coordinate is root 3 over 2, so that would be at 60 degrees, and it would be at 120 degrees. And this is pi over 3. So we'd have 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, so that's also 2 pi over 3. Okay, so we'd have pi over 3 plus or minus 2 pi n, and 2 pi over 3 plus or minus 2 pi n as our solutions. So I'm going to bring the signs all to one side of the equation. So sine squared of x minus 2 sine of x is equal to 0. And we're going to work with this like it's a quadratic function, because it pretty much is. I'm going to factor a sine of x out of each side. So sine of x, not each side, but each term. This would be sine of x minus 2. And if I set each to be equal to 0, sine of x is equal to 0. Sine of x minus 2 is equal to 0. So sine of x would be equal to 2. And over here, sine of x is equal to 0. Well, where is sine equal to 0? My y-coordinates are equal to 0 at 0 degrees and at 180 degrees. Or we could say 0 and pi. Okay, so if I want to write the solutions for this, I would have them be 2 pi n for this one. But it's actually every pi. So it could just be pi times n, right, to cover both of these angles, right? Because every time, when in this particular case, we're talking about here and here, so every time I go another pi, that sounds funny, every time I go another pi, I'm going to be back with sine being 0. And when you look at here, where is sine of x equal to 2, if we go ahead and pop open our calculator and we do 2 inverse sine, not a number, there is no value of sine that is equal to 2, so this provides no solutions. Okay, so this just becomes my solution, pi times n. Okay, so you could have thought of this as, 2 pi n, and then over here it would have been pi plus 2 pi n, but these combine to just be this, pi over n, or sorry, pi times n. Okay, sometimes our equations are in a quadratic type, like the last problem we did, but they're actually talking now about having 3 terms, and we can still factor them in the same manner that we might factor a quadratic function, and also, if we can't factor it that way, we could still use the quadratic formula on these. So an example here, when we talk about, I have 2 sine of x minus 3 sine of x plus 1. So I'm looking, sine squared x minus 3 sine x plus 1. Now I know from this sign that my signs are both the same, and I know from this sign that they're both minuses. Minus, minus. I know the factors of 1 are 1 and 1, so I don't have to think about that. And I know I'll have a sine of x here and a sine of x here. And I'm looking for the products of the factors of 2 and 1 that will add up to be 3. Well, 2 times 1 is 2, 1 times 1 is 1, 2 plus 1 is 3. So it factors really easily to be this. And then if I set each item to be equal to 0, so 2 sine of x minus 1 is equal to 0, and over here, sine of x minus 1 is equal to 0. So over here I'm looking for where is sine of x equal to 1, and over here, where is sine of x, if I add 1 and divide by 2, where is it equal to 1/2? Well, sine of x is equal to 1/2 at, as we've done before, remembering it's the y-coordinate, here and here. So this is 30 and 150. which is also pi over 6 and 5 pi over 6. And where is sine 1? Well, it's 1 up here at 90 degrees, which is pi over 4. I'm sorry, pi over 2. So over here we have pi over 2. So if we want to account for all of these solutions, it would be pi over 6 plus or minus 2 pi n, 5 pi over 6 plus or minus 2 pi n, and pi over 2 plus or minus 2 pi n. Okay, so pretty straightforward. The key thing for you to remember is these things can be factored in the same manner you've already learned to factor quadratic functions. So this is a little different. It's different because of the fact that we've got two different trig functions in here. And so it's going to be very difficult then to make this all sort of combine together. I can't factor it because they're not the same. But what I'd probably want to take a look at is I'd want to go back and look at my trig identities. So from the trig identities, I know that 1 plus tangent squared theta is equal to secant squared theta. So if I take this and substitute it in place of secant squared, I get 3 times 1 plus tangent squared x minus 2 tangent squared x minus 4 equals 0. If I distribute the 3, I'll get 3 plus 3 tangent squared x minus 2 tangent squared x minus 4 equals 0. 3 tangent squared x minus 2 tangent squared x is just tangent squared x. And 3 minus 4 is negative 1. And now I want to isolate my tangent squared x by adding 1. And then I'll take the square root of either side. Tangent of x would be plus or minus 1. And where are my values of tangent plus or minus 1? Well, that means because tangent is y divided by x, it's wherever the x and y coordinates are the same. So it's here and here and here and here. All the multiples of 45 or the multiples of pi over 4. So I'm going to have pi over 4 plus or minus n. Now you notice it's not 2 pi n because it's every time I move. Oh, I'm sorry, that's not true. So it's going to be pi over 4 plus or minus n pi, because every time I go a whole circle, half a circle, I'll get pi over 4, and then 3 pi over 4 plus or minus n pi will take care of these sets over here, and that will be my solution. So if we take a look at this one, it's a little complicated because I've got sine of x plus 1 is equal to cosine of x, and that's a little complicated because I don't have any method of simplifying the sine and cosine like that. So what we're suggesting at this point is if we make it a quadratic by squaring both sides, so then if I square sine of x plus 1, I'll get sine squared x plus 2 sine x plus 1 would be equal to cosine squared x. And again, if I look back at my trig identities, I know that cosine squared x is equal to 1 minus sine squared x. So if I substitute that, then if I go ahead and I simplify, I'm going to add sine squared x to either side. And I'm going to subtract 1. And in this case, if I factor a 2 sine out of each of these, 2 sine of x, this is going to be times sine of x plus 1. And then we want to set these to be equal to 0. 2 sine of x equal to 0, and sine of x plus 1 equal to 0. So where is sine of x equal to -1? And over here, if I divide by 2, sine of x would have to be equal to 0. So where are my y coordinates 0? They're at 0 and at pi, so we're also 0 at 180. And where is sine of x -1? That's at 270, or 3 pi over 2. So I'll have each of these right over here, because it's then every pi. This is pi times n, right? So it'll be, I don't have to do the plus or minus, because every time we go around the circle, pi times 0 is here, pi times 1, pi times 2, pi times 3, pi times 4, pi times 5, right? We'll hit those spots. So this is part of the solution. And then we'll have 3 pi over 2 plus or minus 2 pi n. These are our solutions. Okay, when we work with multiple angle equations, so what I'm going to solve for in this case is I'm going to solve for the sine of 2t, and then I know that by dividing that by 2, I'll be able to find t. Okay, so again, we want to isolate our trig function. Right? And then I'm going to divide by 2. So I added root 3, and I'm going to divide by 2. Sine of 2 times t is equal to root 3 over 2. Okay, and so where is the sine of an angle? Now remember, 2t is my angle. Root 3 over 2, this is again my y coordinate, so that's up here. This is pi over 3, and it's also at 5 pi over 3. Because I have 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. I'm sorry, 2 pi over 3. 2 pi over 3. These are the angles that will work. So if I know that 2t is equal to 2 pi over 3, or 2t is equal to pi over 3, then when I divide by sides by 2, I'll get pi over 6, or here I'll get t is equal to pi over 3. Okay, so then if I want to go ahead and express my answer, I have pi over 3 plus or minus 2 pi n, and I have pi over 6 plus or minus 2 pi n. Okay, so we go ahead and do this one again. I have tangent, 2 tangent of, x over 2, I'm trying to write pi. X over 2 will be equal to 2. If I divide both sides by 2, tangent of x over 2 is equal to 1. So where is tangent equal to 1? Tangent is equal to positive 1 here and here. All right? So tangent is equal to positive 1 at pi over 4. So 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, and 5 pi over 4. So if I know that x over 2 is equal to pi over 4, and x over 2 is equal to 5 pi over 4, I would, in this case, multiply each side of the equation by 2. So x would be equal to 2 pi over 4, which would just be pi over 2. And here, x would be equal to 5 pi over 2. Now, when you think of 5 pi over 2, if pi over 2 is right here, 5 pi over 2, 1, 2, 3, 4, 5, is the same location. So these are actually coterminal angles. So I just need pi over 2 plus or minus 2 pi n. Okay, using inverse functions. So the first thing I would like to do with this problem is I want to factor it. So we're in a quadratic form. I've got tangent squared, I've got tangent, and I've got a constant. So I want the factors of 4, which are 1 and 4, or 2 and 2, and the factors of 6, 1 and 6, or 2 and 3. And I want products of these factors that have a difference of 5. Well, 4 times 2 is 8. 1 times 3 is 3. 8 and 3 have a difference of 5. The larger product, that would be the 8, has to come out positive. So I know I have tangent x plus something, and I have tangent x minus something. The plus will be the 2, and the 4 will have to go in the other binomial, so that when I multiply in this case, my insides, 4 times 2 will be positive 8. And that means this would be a 1, and this will be a 3. So I'll get minus 3. I'll get plus 8 tangent, and I'll get minus 3. That will lead to plus 5. And this all equals 0. So I'm going to set each of these things to be equal to 0. Tangent of x plus 2 equal to 0. And as I go through and solve it, tangent of x equals negative 2. Now it's not as simple as what I was doing before, where I'd pull out the unit circle and I was working with a common angle. This isn't a common angle. So if I look where tangent is negative 2, there's negative 2. So if tangent's negative 2, what angle has that? Negative 63.43, basically 0.44. So I have negative 63.44 degrees. Where would that be? Well, it's going to be over here. But really, that's my reference angle. So what's the angle here? That's going to be 360 minus that. So if I simply add 360 to that, I'll get 296.57. So we have 296.57. Now, with the tangents, it's also going to be the same on the other side of the circle. That will also have the same tangent. And let's just verify that. If I subtract 180, I'll get this other angle, 116.57. And let's just verify that it does indeed have that tangent. If I find the tangent of that, you'll see it's also negative 2. Okay, so here are our two angles. I could convert those into radians if I wanted, but I could also just say it's 116.57 plus or minus 180 n. Okay, because each time it goes 180, it'll be back to being coterminal with these two angles. Okay, now if I take the other part of the equation, right, that was one solution. If I do 4 tangent of x minus 3 is equal to 0, first I'd add 3, then I'd divide by 4. Then if I go through and look where a tangent is 3/4, so I do 0.75 and I do inverse tangent, it gives me 36.86. Well, here's 36.86, but then also I know that on the other side I'm going to have the same thing. So if I add 180 to that, 216.87. So 216.87, and this must have been 0.87 as well. Okay, so now I can also say it's 36.87 plus or minus 180 n degrees. Okay, so in this case I was working in degrees. I could have worked in radians if I'd wanted. I'm not particular about which manner you do this in. If you're really uncomfortable with radians, you could go ahead and switch and use degrees. That would be fine with me. Okay, now the last problem we're going to do is we're going to go through looking at surface area of a honeycomb cell. So they give me a formula to use. And I know they're going to supply me with height. So they gave me height is 2.4, so it's going to go there. And then they've given me S, the lower S here is 0.75 of an inch, so that's going to go there, and it's also going to go there. And then we're going to look for angles. Right? What can we do with this? We're going to look for the minimum surface area, right? So if we look at graphing something like this, we'd look for the minima if we make this into a polynomial. So let's go ahead and take a look at this and see how it plays out for us. Okay, so I'm going to have 6 times 2.4 times 0.75 plus 1.5 times 0.75 squared times radical 3 minus cosine of theta over sine of theta. Okay, so let's go ahead and pull out the calculator to do some of these things. So I'll have 6 times 2.4 times 0.75. That's 10.8. 10.8. Plus 1.5 times 0.75 squared. Okay, that's better. Times 1.5. I'll get 0.84375. And then I've got this thing over here, this radical 3 minus cosine of theta divided by sine of theta. And I have to figure out what am I going to do with that? How am I best going to be able to work with this particular problem? S is equal to this. So in this problem, because what we're looking for is the minimum surface area, this equation is going to yield a wide range of surface areas using values of theta anywhere from 0 to 90 degrees. But we're looking for the minimum surface area. So rather than plug in a lot of values for theta, what would be easiest would be to graph it. And when we graph this, this is what we end up getting. So I didn't pull up a graphing calculator here. But when we graph this, you can find that the minimum for the value of x would be 54.73563 degrees to find the minimum point. So you see you get a curve, a polynomial curve that looks very similar to a quadratic function. And by finding the minimum, you can get the correct result for the angle that creates the minimum surface area. And this, of course, would be the surface area, 11.99, so just under 12 square inches. So for this section, we've gone through describing how to use standard algebraic techniques to solve trigonometric equations. We've gone through specifically quadratic types. We've solved equations involving multiple angles, and we've used inverse functions to solve.